All right, so let us begin. So we will continue from where we left last class. Right. So first we get a relationship for delta x, which is the perturbation in the solution, right? So we have a bound I minus I plus a inverse delta a, right? So and so on, so on. And then we take only this part, right? And then we try to simplify based on what we have already proved in one of the previous classes, right? So we get this 1 minus a inverse delta a, right? But you know a inverse delta a is lesser or equal to a inverse times delta a, right? So if you apply this inequality here, you get I plus a inverse delta a quantity inverse norm is less or equal to 1 over 1 minus norm of a inverse times norm of delta a. So you will get this, right? So you apply this inequality here. So this means minus of that is the other way around, and 1 minus is same, and then 1 upon that is again coming back this way. So you will get I minus a inverse delta a is less or equal to this. But if you look at the answer, you have condition number of a. So we want to bring the condition number of a here. Then what we have is I plus a inverse delta a quantity inverse is less or equal to 1 over 1 minus norm of a times norm of a inverse times norm of delta a over norm of a. So here in this line, I multiply and divide by norm of a. Right? So if I do that, I get this. Right? So right, so I name this as equation 2. Right, so I only take this part and I name it equation 2. Right, so that is less or equal to this. Right. Now I take the other part. Right. I will take the rest. I'll take this together. Right, I'm going to take this part and try to simplify this now. Right, and then I will combine all of them. So if you look at the answer, there also you have a condition number of a. So I can do that. Next, I will take this part. Right, so a inverse times delta v right, so delta a x, right. So now what I do, I want to bring condition number of a. Okay, so I want to bring condition number of a. So this is norm of a times norm of a inverse. Right, so you multiply by norm of a, so you have to divide by this. Okay. So to bring condition number of A, what we did is we multiply and divide by a norm of A. But then you know that in the answer you don't have X. So you have to take this X out. So we will do that in the next step. So this is condition number of A. You know that. Now I want to take this X out. Right? So if I want to take X out, I have to take X from here. There is no X. So I will take it as this. Right, so I will take this, right? But, right, so, but you know that this B is equal to AX, that is less or equal to norm of A times norm of X. So 1 upon B is greater or equal to norm of A, or 1 upon norm of A over norm of X. Right? So you use this inequality and substitute here. Okay. So this is less or equal to this, but for this you use this relationship, right? Norm of B is less or equal to norm of A times norm of X, right? So 1 upon norm of B is greater or equal to 1 upon norm of A times norm of X. So you substitute this, so you get this is less or equal to condition number of A times X. So now if you combine equation 1, 2 and 3, you will get the desired equation, right? Right, so if you combine equation 1, 2 and 3, that is you substitute the corresponding terms from equation 2, corresponding inequalities in 2 and 3 into 1, you get delta x is less or equal to that part. So now if you divide through by delta x, you get the required results, right? So all you need to do is to take this x is common for everything. So you divide by the x here, you will get the perturbation bound. So this is how you prove the perturbation bound by using the required norm, by using the known conditions on norms. So this is called perturbation, right? So there you have input error and output. So then because of the input error, you know that there are some output errors in the output. So you estimate those error by using the known conditions on norm. Right? So this is called perturbation bound. But there are other ways also error can be accumulated. Right? So because of rounding and chopping and other approximation methods, right, which you studied in second year numerical analysis, first chapter, right, because we do rounding and chopping in different number systems, floating point, fixed point numbers, right? So because of that, when you are doing computation using a computer, you will have lots of errors, different errors, and all of them are accumulated together and ended up with the error separate, even if you don't make any perturbation in the input, right? So you know that even if you get all the inputs correct, in that case, you know the perturbation error is not there, but anyways, there will be some errors because of the round offs. Those kind of errors you cannot compute because in most of the cases you don't know the real value, so those errors cannot be computed. So earlier at the beginning of the error analysis section, this chapter 2, we talk about residual, right? So we see that we find residual in a way to estimate the error in approximation. So now what we are going to do is we are going to try to develop some residual error bounds. So we will write that as a theorem and then prove it. Okay, so residual error bound. Right, so this is something we already did, right? So in the case where the error occurred due to some round offs, right? The round off techniques you studied in second year numerical analysis. So in that case, we estimate the error by using the residual. That is the right difference in right hand side between the real right hand side and the computed right hand side. That is R, which is equal to B minus AX hat, where X hat is a computed solution. Right? So we know that is the error. Right? So right, so you notice that E error, right? So you know that E is error, so I don't need to mention it again. Right? So E means error is X minus X hat, the real solution minus the computed solution. So the relationship between the error and residual is equal to A times the error, the coefficient matrix times the error. So now we will see the residual theorem. Right? right? So then right, so in this case, first part, error is bounded by A inverse times R. R is the residual and A inverse is the inverse of the coefficient matrix A. And also, second one, the relative error E upon X is bounded below by 1 upon condition number of A times norm of R over B and bounded above by condition number of A times R over B. So we shall prove this one by one. The first one is easy, right? Because of this, right? So you know that, so that's quite obvious. I will just write it down. So E is equal to, sorry, R is equal to AE. So E is equal to A inverse R, right? Because R is equal to AE, we know that it is E is equal to R A inverse R because A inverse, assuming that A inverse exists. Right? So norm of E is equal to norm of A inverse R, that is, let's say, equal to norm of A inverse and norm of R. Right, so this is one of the estimates for the error. Norm of A inverse and norm of R. Now we will prove the other one. Right. So we have a two-sided inequality. We will try to prove both sides, right? So okay, so right, so first we will consider E upon X, right? So E is less or equal to A inverse R. Okay, so you know that E upon X is less or equal to A inverse times R over X by using the first result, right? So this one you use, that is less or equal to this, right? But you know you want to get condition number, so you have to put an extra A. So that is actually norm of A times norm of A inverse times norm of R over norm of A times norm of X. Right? But you all know this. B is equal to AX, but that is less or equal to norm of A times norm of X. So if you combine both this thing, you will get norm of E over norm of X is less or equal to, this is condition number, norm of R, and this one is less or equal to 1 upon B. Okay. So we prove the right side inequality. Right? So this side we prove. Now we have to prove the other side. Right? So E is greater or equal to what? Right? So next, again, I use R is equal to AE. So norm of R is equal to norm of A times norm of E is less or equal to norm of A times norm of E. Right? So norm of E over norm of X is greater or equal to norm of R over norm of A times norm of X. Okay? So you take E here, put it E, bring this A here, but 1 upon X, so 1 upon X. Right? So you have this. So now what you have to do, you have to rearrange this to get a condition number below. Right? So but you know that Ax equal to B. So X is equal to A inverse B. Right? So you take norm, you get X is equal to norm in A inverse B, that is less or equal to A inverse times B. So 1 upon X is greater or equal to 1 upon norm of A inverse times B. So now you combine this and that. Then okay, so you combine this inequality and this inequality. 1 upon X is greater than or equal to 1 upon A inverse times norm of B. Right, so you combine them, you get this. But this is condition number. Right. So this is 1 upon condition number of A times norm of R over B. Okay. So if you combine 1 and 2, you will get the results. Right. Okay. So you get this. Okay. So this is the error bound, right? Perturbation error bound. First we see this is a general error bound. So we define the relative error, or we bound the relative error in terms of residual and the condition number and the right hand side vector. Right? So B, R, and C. So now we talk about this condition number thing. Right? So we have this. We define what do we mean by condition number? It is norm of A times norm of A inverse. So here it is used as a number to estimate the errors. So now, but the name condition number comes because it basically defines the condition of the system. Right? So because the condition of the system means the stability in a way. Right? So we see that there is perturbation. So there are there are possibilities of input errors. So there can be some systems where you make a small mistake in the input, right? Just like 0.001, you put it as 0.0001, right? So just a small mistake in the fourth decimal place. But that mistake, that small mistake might give you a large mistake in the solution. Right? Even though you make a small mistake, it is possible that for some systems it will lead to a very big mistake in the solution, right? Relatively very big mistake. So to see whether the system will give you that kind of problem or not, we can use the condition number. Right? If the condition number is small, then we can expect that even for a small change in the input, the solution may not change by big number. But if the condition number is large, then we say we can expect that there will be a big change in the solution for a small change in the input. So for those kind of systems, we will define ill condition and well conditionedness of a system, right? So that is the last section of this chapter 2. So I am going to define the condition of the system. Okay, so if the small change in the input leads to a big change in the solution, then we say that the system is ill conditioned, right? If it leads to a very small change in the solution as well, then we call the system as well conditioned, right? So if you want to prove a system is ill conditioned, then you have to show that for a small change, there is a big change in the input, especially in the coefficient matrix A, the solution changes by a big margin, right? So we will see an example of that. Okay, so you have a system like this. Right, 1 to 0.499, 1.01, x1 x2 is equal to 3 comma 1.5. Sorry, 0 0 1. Okay, so you have a system like this. So now you know Gaussian elimination, no pivoting, nothing, just Gaussian elimination. You can apply and get the solution. Right? So this gives you x1, x2 is equal to 1, 1. Right? This is the real solution. Right? Real system, real solution. Right? No issues. You can easily compute this. All right. So by using Gaussian elimination, you can compute this. So I am skipping the part. Now, let's do this example. So now we slightly modify it. One small mistake, right? 0.499 is inputted as 0.5. So the mistake is 0.001. That is the only small mistake. So now if you solve this, right? So you know rho 2 minus 0.5 times rho 1 gives you this 1 2 0. So 1.1 minus this. So 0.001. Right. So now if you apply Gaussian elimination for this system, right, R2 minus 0.5 times R1 gives you this 0.001 is equal to this. So now okay. So now the computed solution is right. So I will write it as x hat. That will be 3 comma 0 because you know x2 is 0 and then x1 will be 3. This is your computed solution, right? So now you can see that perturbation in A, delta A, right? According to my notation, that is the error in A. So that is 0, 0, 0.0010. This is the error in A, right? But error in X, right? Delta X is 3 minus 1, 1 minus 0, right? So that is 2 comma 1. Okay, so 2 comma 1, right? So now you know the error in the input and this is the error in the output, right? So now we can see that obviously from this you obviously know for a very small error in the input you have a big error in the output, right? So you can justify it with the norm, right? So we will take column sum norm or whatever, right? So we will take norm. I'll take delta x1. So that is absolute value of 2 plus absolute value of 1 is 3. Right? X is 1 plus 1 is 2. Or infinity now, that is easy. Right, so we will take infinity now. So it is a maximum of 2 comma 1, that is 2, and this is 1. Right? Infinity norm of delta A, that is maximum row sum, so that is 0.001. Infinity norm of A is maximum row sum, that is 3. Right? So now you look at the relative error. Delta A over norm of A is 0.001 by 3. Right? So that is 0.0003. And norm of delta x over x is 2. So for a relatively small input error, you can see that relatively big output error, right? So relatively very small input error, the output error is very big, right? So sometimes you cannot look at the numbers and tell, right? Numbers might look very close, but if you look at the norm, right? Same norm you have to apply, so that is why I apply infinity norm, because in infinity norm in vectors you take the maximum, in the infinity norm in matrix you take the row sum, right? Maximum row sum, so that is easy for you. Even you can do column sum, but that will give you a lot of decimal numbers, so that is why I change back to row sum. So now you can see that small input change, very big output change relatively, so this is ill condition. So this system is called ill condition. So this is how you determine the condition of a system, right? Well condition and ill condition of a system. Right. So now this concludes chapter 2. So we will try to post a tutorial on chapter 2 soon. And we will start chapter 3 in the next class. That is about a different method to solve system of linear equations. So far, we talk about elimination methods, right? In the next class onwards, we are going to see some different methods to solve system of linear equations, right? So I will stop here and start a new chapter in the next class.